Right, recording is rolling. Welcome to Wednesday. So today I want to clean up some problems that it hadn't got quite to in the notes. We'll finish those chapter problems from the homework. There's a couple other things I want to mention, and we'll do a Kahoot too. Now it's going to be a tight fit, but we'll get everything in. So yeah, we're doing Kahoot today, and I won't see you guys tomorrow because Veterans Day. But when you guys come back on Friday, we'll do a coefficient of recitation lab. I'll mention that in the class today. We have a minute. Right, so, you guys know I passed back your energy quizzes to your folders back there. If at some point you want to run back there and get your energy quiz, if you need to do corrections, something like that. I know there's a interim grade coming up pretty soon. So, right, before we do the book problems, I want to mention this triple beam balance because on your guys' Open Notes take-home quiz, you may have noticed that there's a slight typo related to that. But here, so show this up here first. And so this is a device to measure mass, and it works on the principle of torque, which we haven't studied yet in this class, but I bet you guys can sort of get this. Okay. So you guys see these three beams? Oh, that's why it's triple beam, right? It's a triple beam balance. And so you take, say, this pin. I want to get the mass of this pin, right? So, over here, hopefully you guys have gotten your hands on this at some point. I've had this out sometimes, right? This needs to level out to 0. Okay? So if I put some object on it on both sides, it's going to go like chimp like that. Okay? And then I take these sliders. Here's 1 gram at a time. Here's 100 grams at a time. This back one's 10 grams at a time. Okay? And try to restore balance. So this pen, and this is not the best fit for either of these cameras, is I think pretty much exactly, well, it's like either 10 grams or, yeah, it's like pretty much exactly 10 grams is what this pen comes. No, yeah, 10.5, something like that, grams, right? Right. Now, guys, since this works on principle of torque, I mean, you can imagine like you and a friend are on a seesaw. If you like back up against the seesaw, that's like sliding one of these. Doesn't that like tip it more towards your side? Like, if I took this whole device to the moon, which has very weak gravity, there's still gravity on the moon, just very weak. Right? Would this pen still read about 10 grams on the moon? Yes, it would, right? So the gravity field ends up canceling out both sides. Why did I bring that up? Because on your guys' take-home quiz, there is a small typo, but it's the type of typo that if you wrote this term on the on your actual FRQ AP exam, they probably count it wrong because it's just one of those things. Okay. Question number 2 says you want to determine the impulse. I should have said on a ball. Impulse on the ball bouncing off the floor. You're allowed to use exactly 2 of the following 4 measuring tools. This is an AP style question, right? So you want to set up an experiment. What measuring tools do you need? Okay. Now you could use any collection of these. Well, I gave you guys 4 measuring tools, and any of them could be used to figure out the answer to this question. What is the impulse of a ball bouncing off the floor? Okay. But there's one tool that you absolutely have to use. Okay. And one of the options I typed was triple balance beam. Now, if you write triple balance beam, that's something they could count wrong. That's not what it's called. It's called triple beam balance. Okay, you guys got that? Okay. And I wasn't originally planning on giving you guys any hints on that question, but since I'm already talking about it, here, sort of throw some ideas at you guys. Okay. So, a ball bounced off the floor. Boing. Got this ball bouncing, right? Ball bounced off the floor. Okay. So, what would the force associated with that be? Well, I know that force times time interval, that's really average force, right? Average force times time interval is equal to mass times change in velocity. Something to do with that, right? Well, here's the mass of the ball, m. Okay. Change of velocity would be like final minus initial. Here's the final. Here's the initial. Okay. Thinking about that, let's see if you guys remember this. Suppose that the drop speed is like 10 meters per second, and the rebound speed is like, say, 4 meters per second upward. So 10 down and 4 up. Okay. What is the delta V of that ball bouncing? And it's not 6. It's what? 14. You guys see 14 meters per second? Because it's 4 up minus negative 10 down, right? So 4 minus negative 10. Maybe I should say negative because, if you think about vector directions, right? Okay, you guys see that? Okay, so that was sort of feeding here. What can I rearrange this? Actually, this would be here. Actually, all I asked you guys in that question was to solve for the impulse, and that is already set up to solve for impulse. Okay. So now you're thinking about measuring devices because you want to set up some experiment where you can figure out the answer to that question. What's the impulse, right? Now, how could you get these speeds, like these speeds? I can think of many ways to get those speeds. Right? You could now, if you had a motion detector, you could get it directly. You could just get a direct reading about the crash, a direct reading about to after it's rebounded, and then solve for delta V that way. Right? You could measure drop height and rebound height, right? And figure out speed that way. Maybe use conservation of energy. I bet the speed is equal to square root 2gh, right? Right? You guys have seen that many times before? Right? I bet you could even have a stopwatch, and you could calculate the time that it takes to fall and the time to rebound to its max height. Now, that would be a really awkward way to do it and probably not very accurate, but in principle, you could, right? How much time? That's 3 different ways where you can get this delta V. But can you use the stopwatch or the meter stick or the motion detector to measure the mass of the ball? Right? Okay, you guys sort of see where I'm going with that question? Right. What's it? Oh, there was another detail I want to mention about this too, because I made this at like midnight a couple of minutes. So, question number 4. Yeah, I typed this question and realized after the fact this is a pretty tough question, but only because it has lots of little parts to it. Okay. We got Alan and Bob standing on frictionless ice, and they're throwing this snowball back and forth. And you know all their masses: mass of Alan, mass of Bob, mass of snowball. I gave you some throwing speeds. Right? They're throwing it back and forth. And the question is, after this process of throwing it back and forth, catching a snowball, how fast are they moving away from each other? So I've been going back and checking my answers, and I think it made one tiny error, but not something that throws it off very much. So if you use completely correctly, you might get an answer that's off from my answer choice by about like 1 or 2%. So we'll just go with whatever's closest. Okay, so I'll keep this as a question. It's involved in the sense that you have to have lots of small parts to it, but the answer is probably off by about 1 or 2%, but that's not really enough to throw it off by a whole lot. Okay. All right, good. Good with that. And the other one I do have to mention on this is this ballistic pendulum, but that's one of your homework problems that I will go over today. So you guys are about to see that in a few minutes. Okay. All right, let's hit those book problems, the last few, and there are 3 that I have to go over. So there's number 42. We got this car crashing into this van. You know the mass of each vehicle, you know the pre-collision velocities, and then you're told after the crash, the bang, what the post-collision velocity of the car is. Can you figure out the post-collision velocity of the van? So this one actually I don't think requires a whole lot of thinking. It's just pretty straightforward general conservation momentum. So number 42, sum of momentum before the crash is equal to sum of momentum after the crash. Hey, if it's a collision, you know it's going to be conservation of momentum, because if you used any other method, it would just give you a wrong answer for the reason we talked about. So we got mass car, velocity car initial, plus mass van, velocity van initial, equals mass car, velocity car final, like post-collision, plus mass van, velocity van, like post-collision. Okay? And out of all these, the only thing that you don't know that you're solving for is the post-collision velocity of the van. Okay, so let's just do some plug and chug, right? So we're just doing momentum accounting. I'm going to call my car 1,000 kilograms, which shows up there and also there. And I'll call the van 2,000 kilograms. 2,000, yeah, which shows up there and there. Right? Now it's different than the book numbers, but that's usually how I do these things, right? I'll have you know what? I just saw this before and I made up some numbers that worked out really nice. So let's see if I can find it. Oh yeah, here we go. Okay. Let's say the car was going at 25 meters per second, and the van was going 20 meters per second. Right? The van's going slower. That's why the car rear ends into it like the van, right? Okay. Add that together, you get the total momentum beforehand. Okay? And then, no, if I only gave you that information and nothing else, then you wouldn't be able to solve this. There's still a lot of possible things that could happen. Okay? If the cars coupled together, then you might call this inelastic, and you could solve that. right? Because these would be the same velocity. You just factor that out. Okay? But this is not perfectly inelastic. So I'll tell you, maybe the post-collision velocity of the car is like 19 meters per second, maybe something like that. Just make up a number. Okay, so what's all the momentum before the system? Or sorry, before the collision in the system? We're going to treat this as a closed system, right? So it'd be 1,000 times 25 plus 2,000 times 20. Okay. I'm looking at 65,000 kilogram meter per second of momentum that's in the system. Okay. Now that's before the collision, but that's also after the collision because momentum is conserved. So 19,000 units of momentum when should the car post-collision. Okay. That left everything else for the van. 2,000 kg times some VBF. Post-collision velocity of the van. Okay. And so subtract off the momentum that went to the car and you're left with what went to the van, divide by the mass of the van, and you should get it. Okay. So what's 65,000 minus 19,000? Okay. That leaves 46,000 units to go into the van. So velocity of the van post-collision is those 46,000 kilogram meter per second divided by the mass of the van, which is 2,000 kilograms. That is 23 meters per second velocity van final post-collision. 23 meters per second. Notice that the van did get a boost, didn't it? Because it was going 20 before the collision, and then bam, gets a little bump, goes a little faster. Okay. But I've got another question for guys, which is, actually, they asked this anyway. How much mechanical energy was lost? Okay. Now, mechanical energy, that could be potential energy, but I don't see any springs or any height changes. Could be kinetic energy. That's actually probably what they're talking about, right? When you say mechanical energy for this question, it's actually kinetic energy, energy motion. Now, guys, is the kinetic energy conserved before and after? No, right? Unless it was perfectly elastic, but that's probably not the case. So let's run the numbers. What should 1/2 mv squared before and after? So kinetic initial was your, I'll say, sum of 1/2 mv squared. Okay. So that's 1/2 mass car velocity car initial squared plus 1/2 mass van velocity van initial squared. Okay. I'll just plug in the numbers on the calculator screen because we're kind of short time today. Mass of the car was 1,000 kilograms. Velocity of the car initial, I said, was 25 meters per second. Square that. Okay. I'm looking at, let's do on one line. Okay. Plus 1/2 times mass of the van, 2,000 kilograms, times velocity of the van initial was 20 meters per second. Square that. Okay. That is, looking at 712,000 some joules of energy. Okay. That's before the collision. Okay. Let's check after the collision. Okay. So if it happens to be perfectly elastic, then it would be 712,000. But anything else, it has to be less. Okay. If it's more than, then well, something's wrong. Okay. So that's your, but same setup, just different numbers. Okay. So sum of 1/2 mv final squared, okay. And that is 1/2 times 1,000 times, let's see, post-collision velocity of the car was 19 meters per second. I'm just drawing these numbers from before. Okay. Plus, what's going on here? Okay, 1/2. Okay. 1/2 times 1,000 kilograms times 19 meters per second being squared, plus 1/2 times 2,000 kilogram times, and then here's where the answer we got was 23 meters per second. You guys remember that? So 23 meters per second being squared. Okay, so we did all that conservation momentum just to get this number. Okay. Now I'm using that to check the kinetic energy. Okay. And, 709,500 joules. Just like that. Okay, so there's before, there's after. So delta K, the change in kinetic energy, it looks, final minus initial, looks like negative 3,000 joules, right? Which kind compared to the total kinetic energy, it actually is not that much of an energy change. So it looks like actually this collision was pretty close to the elastic end of the scale, isn't it? That was a pretty bouncy collision going on right there, which is I don't know, maybe good news for the cars themselves, because not a whole lot of energy went into like crunching the cars. Although if you're riding in the cars, that'd probably be worse for you, right? Because the cars didn't absorb a lot of that energy. Right? Like bouncing, there's usually more force associated with that. So that'd be bad from a person point of view, but maybe good from a car preservation point of view. Okay, next question, number 49. Got another car crash. 2,000 kilogram car moving east at 10 meters per second collides with a 3,000 kilogram car moving exactly north. So one moving east, one moving north. The cars stick together and move as a unit after the collision at an angle of 40 degrees north of east at a speed of 5.22 meters per second. Find the speed of the 3,000 kilogram car before the collision. This is an excellent type question if you are going to be a forensic investigator one day, and you might see some car crash and some tread marks on the road and say, I wonder how fast so-and-so was going before the collision. What led up to this? So I'm just going to go ahead and use the book numbers for this one, as I'm going to explain it's a bit faster than I normally do, but only because I want to save some time here. Okay. So let's start with, I think I can solve portrait right this way. Start with the diagram. So number 49. So we got an east-west axis that, okay, maybe I'll call it like the x-axis, right? But this is like east. Okay. And then I've got a north-south axis. Okay. So I'll call it like the y-axis, right? That'd be like north. Okay. Oh, whoops, sorry. Gotta zoom out. You guys can see what's going on. Okay. North-south axis. East-west axis, but I'll call this X and Y, something like that. Okay. We got a couple of cars. I've got a car and a van, I should say. Right? So there's a car with some momentum this way. I'll do momentum in the X direction. Okay? And we got a van coming this way. There's momentum in the Y direction. Okay? And they're going to collide, I'll say, at the origin point of this made-up coordinate system they made. Bam! Okay. How did I know to make the Y direction momentum a little bit less in magnitude than the X direction momentum? That's where the 40-degree angle comes in, because they're going to, bam, move off at, remember it was 40 degrees north of east? Yeah. Okay. And they told you the speed, but post-collision speed, but we'll use that later. Right. So I will call this momentum final, P sub F, momentum final. Okay, is that right? Now, in your mind, you could think, or if you're doing this as an FRQ, which actually AP is not big on two-dimensional collision questions, so this probably would show up, but if it did, you guys know if you really have to draw component vectors to make sure you dash them. Right? But AP prefers you don't draw them all, but something like that. Isn't it true that this component has to all come from this van? And this component has to all come from this car. That's how I knew to make P sub Y less in magnitude than P sub X, because 40-degree angle is less than 45 degrees, right? Right, so we're going to need a system of equations to solve this. I know that the sum of momentum in the X direction is conserved. Therefore, I can say that this initial momentum from the car is equal to P final times cosine of 40. No. I'm so sorry. Scratch. Rewind. Right. Let's go back to. I got some space up here. Okay. I meant to do the Y direction first. There's a specific reason I meant to do Y direction first. Okay. Let's put this up here. Okay. This is conserved. So P sub Y is equal to P final times sine of 40 degrees. And then here's the setup for this one, do cosine 40 degrees. Okay. So here's your system right here, system of equations. Wouldn't that be clear? You guys get that like on the face of it? Okay. Right. Then what is that momentum? Well, it's just mass times velocity. Right? So I got here, this is referring to the van, this is referring to the car. Okay. So in the y direction, the mass of the van times the initial velocity of the van, okay. That's this top equation. Okay. That must be, okay. Now P final, well, that's the sum of the masses because so mass car plus mass van, okay. Because inelastic collision. Okay. All times the post-collision velocity times sine of 40 degrees still, right? And then the second equation was this is the x direction now, mass of the car times the initial speed of the car, or let's say initial velocity of the car. Right? Right. Then post-collision, you got the two combined, car plus van times the post-collision velocity times cosine 40 degrees. Okay. So there's your system again. Okay. First equation, second equation. Okay. So first way I wrote it is really more like a formulate way, and now I've got the equations. Okay. Well, sort of. I never plugged in the masses of these things. I did plug in the angle. Okay. Here. You know what? Since you guys are AP, I should just do everything in terms of variables, right? So instead of 40 degrees, let's call it theta. Okay. Then you can plug in the numbers after the fact. Okay. Wait. What's going on here? Is that okay so far? Solve in terms of variables. Okay. Now, what's the question? The question is, what's the yeah? What is the pre-collision velocity of the van? That's what we're solving for. Okay. And supposedly you should know everything else. They gave you the mass of each vehicle. They told you this angle was 40 degrees. They also told you the post-collision speed and the speed of the car. Right? So you know everything except for that. How do you solve for that? Okay. So this is how do you solve a system of equations? Well, we've sort of got the physics down already. So how do you do the math? One way you can solve the system of equations is divide one equation by another equation. So what I just drew in pink ink are fraction bars. I'm just going to divide one equation by the other equation. Okay? So if you do that, then do you guys see that the post-collision velocity is going to cancel out? So, and what is sine of theta divided by cosine of theta? That's tan theta, isn't it? Tan theta. Oh, also, sorry, this whole thing cancels out. There's mass car plus mass van. The combined mass cancels too, right? Okay. So I've got mass of the van times velocity of the van, which we're solving for, divided by mass of the car times velocity of the car is equal to tangent of that angle. Okay. So velocity van is equal to, I'll just multiply this stuff up. I got mass car, velocity car, divide down mass of the van, and then you still got your tan theta. Okay. That's the answer in terms of variables. Let me plug in the numbers they gave you, just make sure that this does check out. Okay. So they told you the mass of the car was 1,000. No, they didn't. They said it was 2,000 kilograms. 2,000 kilograms. Okay. They said the initial velocity of the car was 10 meters per second. Okay. So divide by the mass of the van was 3,000 kilograms. Okay. And multiply that all by tangent of 40 degrees. Okay. Yeah, that's it. That's the answer. Okay. That tells you how fast the van was going before that collision. So conservation of momentum, 2 dimensions, system of equations, boom, boom. There you go. All on one page. Yes. Oh, yeah.
Why do you have to do the system of equation stuff at all? And why can't you just plug in the values for the V-van equation?
Okay. Think if I can think about that. Because the motion of the car also matters. So if, say if the car had been going faster, then this angle would be less than 40 degrees. Or if the car had been more massive, it also would have been less than 40 degrees. So the physics of the car does affect the post-collision motion of the vehicles also. Yeah, so you have to consider both.
But they give us the post-collision statistics.
Oh, you know what? I think you're right about that. Did they tell you post-collision velocity?
Yes, they do.
Oh, okay. Actually, you could solve it that way then, couldn't you? Yeah, that is true. That is true. The fact that they gave you post-collision velocity, yeah, you could solve it that way. Right. That's a good point. Yeah. Different way to solve that. Right. So one more I have to cover with you guys, and that's the ballistic pendulum. Right, you guys ready for a ballistic pendulum? Right, so I'm gonna present screen to share. I got an animation for you guys. This is a classic physics question right here, ballistic pendulum. Okay. Now, I haven't researched the history on this, but I have a pretty good guess of what the history would have been. Because, okay, did you guys just see a bullet being fired into that block, and that block swings up some angle, something like that? Okay. The question that's usually asked about this is, what is the firing speed of the bullet? In fact, that's a really opportune question, because everything else is easily measurable. Think about what else that you could measure. You can measure the mass of the bullet, just throw it on a scale. You can measure the mass of that block, throw it on a scale. You can measure the length of that pendulum, right? Use a meter stick. You can measure the angle it goes to, use a protractor. Right? Those are like very easily measurable quantities, right? But the speed of that bullet, well, that's a little trickier. But I bet you could calculate the firing speed of that bullet, right? Based on all those other numbers. Wouldn't that be true? Right? Imagine it's like 1800. It's 1800. You have some shiny new pistol. You got to figure out what's the firing speed of this pistol, right? Well, that would probably the easiest way to solve this is to use physics, right? And so that's what we're going to do. Now, the way we're going to solve this is going to be in two parts, right? And we're going to solve this in reverse chronological order, because what we're solving for is chronologically the first thing that happens is that the bullet is fired. So what are the two parts? Well, I see a collision, so that would be conservation of momentum. But after that, see how the block like swings up to some height? So that's like, a pendulum swinging up to some height. Hey, that reminds me of last section, conservation of energy, doesn't it? Remember, like the guy swinging? Okay. Now, you guys were asked that backwards. It's like, well, if you fall some height from a pendulum, what's your speed at the bottom? But this is just that in reverse, isn't it? Okay? Which is exactly how we're going to solve this thing. So, see, stop sharing, switch back over. All right. And ballistic pendulum time. Ballistic pendulum. All right, so what do you guys just see there? You know what? Let's do this. Let's use a portrait. There. I'm going to call the block mass capital M, okay? And it's going to swing up to like up here because it had a bullet fired into it. Okay. So here's mass. Well, mass of the bullet I'll just call little m. Okay? And then there was some firing speed I'll call v sub bullet. V of the bullet. Right? And that's what we're solving for. We're trying to figure out what's the firing speed of this thing. Okay? So that this block swings up like some height change. Except the way I gave it to you in your on your take-home quiz, and also what you saw in the animation, is instead of getting the direct height change, instead you know the length of the pendulum and the angle it swings up to. But you guys know you can't solve for that, right? Do you guys happen to remember, if you go through the geometry, and I'm doing this faster than I normally do because got a tight fit this week, but you guys remember back in your notes from the other day that the height change is equal to, does anybody remember the expression for that in terms of L and theta? L times, yeah, L times 1 minus cosine theta. Yeah. Okay. So make sure you can do that, because I'm thinking that this ballistic pendulum would probably be a really good FRQ question that AP could actually give you, and they would expect you to be able to solve that based on the geometry. Okay? So you guys have the notes for that already. Okay? We're solving for this. Okay? So we're going to solve this in two parts in reverse chronological order. Okay? So part one is we're going to apply conservation of energy. Sum of energy initial equals sum of energy final, just for that pendulum part. Okay, so it got kicked up some height. So how fast did it have to be going to get there in the first place? Right, now, after the collision happens, what kind of, and the bullet would be embedded in the block up here too. Okay. What kind of energy does the block have at the bottom as it's about to start swinging? Or I should say, as it is swinging, really. A lot of what kind of energy? Kinetic. Right? Then when it swings up to its maximum height, it has all what kind of energy? Potential. So we've got some 1/2 mv squared. No, the m, I'm going to say this is after the collisions happen. So the bullet is embedded in the block. V post collision squared goes to mgh, just like that. Wouldn't that be true? Right? Kinetic goes to potential for a pendulum. Right? You guys see that? Now, even if you miss the detail about what mass is relevant, you guys see it's going to cancel out anyway, right? And suppose you solve for what is the post collision velocity? Like, how fast do they have to get swinging to swing up to that height? Let's solve for that. Cross multiply of 2, take the square root. V post collision is equal to, oh, it's square root 2gh. Square root 2gh. Right? No surprise, right? Of course, if this were an FRQ, you'd have to show that, but no surprise, you guys have seen this so many times in this class. Right? Let's go one more step. In terms of L and theta, that's the square root of 2gl 1 minus cosine theta. If you go do the geometry, you guys should be able to figure that out. Okay. Right, now, that's not the firing speed of the bullet, but let's hold on to this. I'm going to dash outline this because that is a critical middle step. Okay, right there. Right. So that is part 1. Right. We use conservation of energy to figure out what the post-collision velocity was of the bullet and block swinging together. Okay? And it's that expression right there, square root 2gh. Okay? Okay. Part 2. Let's apply conservation of momentum. The sum of momentum before the collision equals the sum of momentum after the collision. Because that bullet embedding itself in that block, you have to use collision physics, which is conservation of momentum. Okay? So didn't all the momentum come from the bullet in motion? Because the block was just at rest, right? So I'm going to do mass of the bullet, well, just a little, right? Times the firing speed of the bullet, which we're solving for. I could say plus mass of the block, velocity of the block, but that's just 0 anyway. Right? Equals, right? So here's where all the momentum came from. Where did it go to? Oh, guys, this collision is perfectly lit. Inelastic. Block plus bullet times V post collision. Right? Okay. And you have like either given or measured or easily measured values for mass of the block and mass of the bullet. Right? But and we're solving for the firing speed of the bullet. So how fast do they swing together? Oh, well, that's what we did all this stuff for. All this conservation of energy. So all you have to do is take this expression and substitute it right in there. So, boink, it's right in there, right? Is it? And then there's one algebra step besides that, which is to divide both sides by mass of the bullet. So velocity bullet ends up being, okay, we got post-collision momentum, which is this expression now. Square root 2g, well, h is L1 minus cosine theta. And then you divide that by the mass of the bullet. There's, I'm going to write that just a little bit prettier. Right, so I'm not writing anything new, just making it look a little bigger. M plus m over m. There you go. That is the answer in terms of variables. What is the firing speed of a bullet for a ballistic pendulum? If you know the length of the pendulum and you know the angle it goes up to. Yeah.
How come you only divided the one side of it by the mass, not the root 2 GI or anything?
Okay, so it's associative property of multiplication. So whether I group this together and multiply it by this expression afterwards, or if I just like do it all in one go, like this is still sort of like in the numerator of this fraction. Okay. So yeah, this and this are slightly different ways of writing the same thing. Yeah. So here it says. So whether it's like a times b all divided by c, that's the same thing as a over c all multiplied by b. It's the same thing. And right, so everybody good there? All right. Make sure I got everything. Okay. I think we're ready for Kahoot. You guys ready for Kahoot? So switch my screen over. Say play, Kahoot, teach. Send screen to share. Kahoot, classic. All right. Okay. All right, so 1148667 is your pin. All right, here we go. Momentum of an object is defined as the object's mass times velocity. Yep, mass times velocity. I'm gonna do this a little bit faster than I normally do. If momentum of an object changes, but if mass is the same, then it's hold on. What is the 1148667.
All right.
Right? Yep. Okay. Okay, so if momentum is changing but mass is constant, that means its velocity is changing. But if its velocity is changing, that means it's accelerating. And if it's accelerating, that means there's a force on it. So these options all reiterate each other. If one's true, they all have to be true. Table tennis ball launcher is fired. Compared to the force on the ball, the force on the launcher is. Yeah, that's Newton's third law of motion. For every force, there's an equal and opposite reactive force. Now, why am I mentioning that? Well, take a good look at that impulse. That impulse poster up here. You guys see that one? Okay. So the launcher and the ball have the same force on them, right? Okay. And would that force also act for the same time interval? Okay. This. Paul Hewitt on fire. Right, so same scenario. Compared to the impulse on the ball, the impulse on the launcher. It's also the same, right? Same force for the same time interval, same impulse. Right? You could also interpret that as mass times change of velocity. So the mass times change of velocity of the ball, one direction, is equal to the mass times change of velocity of the launcher in the opposite direction. Because momentum is conserved. Ooh, Juliet on fire. A collision is elastic if yeah. Okay, so the definition I gave you guys is that kinetic energy is also conserved, right? But that also implies these other things, right? Because the blue one is inelastic, if they did stick together, right? And if some of the energy did go into deformation, then that would divert it away from kinetic energy. Right? So, there you go. All right, come on fire, Juliet, leading the pack. Suppose girl standing on a pond where there is no friction between her feet and the ice. How can she get off the ice? Yeah, if there's something opposite. Oh yeah, look at you guys go. You guys remember that magic school bus clip, right? It's hard to run around on that field unless either you threw something or something hit you. A freight train goes along a track with momentum. If it were to roll same speed but had twice the mass, its momentum would be twice as much, right? Because P equals mv. So you double the mass, double the overall momentum. That's a direct relationship. All right, Juliet still in the lead. We've got Vanilla on fire. Cannon recoils from launching a cannonball. The speed of the cannon is small because why? Yeah, just go, right? Because the cannon has so much mass, so much inertia, right? Either from an impulse point of view or from it would have less change of velocity, or from the old way of thinking of it, would have a small acceleration. Either way you think of it, right? But the force is the same, gets the cannon into the cannonball. The impulse is the same, opposite directions. And yeah, okay. All right. You guys got that. In order to catch a ball, a baseball player moves his or her hand backward in the direction of the ball's motion. Doing this does reduce the force of impact. Why? Oh yeah, you guys did really good on that. Right, time to impact is increase. Okay. The impulse is actually not changed regardless of how you catch it. I'll show you guys why. So, you got a baseball, and you catch that baseball. Okay, so, bring its velocity to 0. Okay. Think about what's going on with the impulse. So, average force for some very small time interval is equal to mass times change of velocity. Now the mass of the ball is whatever it is, that doesn't change. But also the change of velocity doesn't change either, because it was going some really fast speed and now it's going 0. Regardless of how you catch it, this whole side of the equation is some constant value. For example, maybe like 24 Newton seconds. I'll just make up some numbers so you guys can see this. Right? So what if you, just to deal with integer values, caught this thing in like 2 seconds. Right? So it hits your glove and you pull it back your hand and bring it to a stop in 2 seconds. What was the average force? 12 newtons. Right? What if instead, because you can't change anything on the right side here, mass of the ball doesn't change, its change of velocity doesn't change. Right? What if you did it in 3 seconds? What's the average force?
8.
Ooh, 8 newtons. 8 newtons. Right? Do you guys see if you increase the time interval, that decreases the force? Okay. 2 variables multiplied together on the same side of the equation have an inverse relationship with each other. Juliet still keeping that lead. Car traveling along a highway needs a certain force to bring it to a stop. You need more force when the car has Yeah, all the above. Mhm. Oh, I like this question. Force of an apple hitting the ground depends on. Draw this out. Oh, good call. You guys got that. So force times time interval equals mass times change of velocity. Okay. So what is the force on that apple? The boing bouncing off the ground? Well, has something to do with that, right? So we've got the mass of the apple, that matters. Okay. Whatever its crash speed was, v crash, that matters. V rebound also matters, right? Because isn't delta v, this change of velocity, the difference between these two? Okay. I'm going to make up some numbers. I wonder how many guys are going to get this. What if it crashes at 10 meters per second and it rebounds at like 4 meters per second? What is its change in velocity? And it's not 6, it's 14 meters per second, right? 4 minus negative 10. Okay. So rebounding definitely would make a difference too, wouldn't it? Because it would change this part right here. Okay. Time of collision. Okay, you guys got that right. All right. Moving freight car runs into an identical car at rest on a track. The cars coupled together. That's inelastic. Compared to the velocity of the first car before the collision, the velocity of the combined cars after the collision. So you got like 10 meters per second, and then bam, equal mass. Don't they roll off together at like 5 meters per second if they had equal mass? Say 1 kilogram times 10, that's 10 units. Okay. Then bam, now we're up to 2 kilograms. 2 times 5 is also 10. It has to be half as much. Is that okay? Okay, just apply inelastic collision. Oh, piece of putty, moving with 2 units of momentum. Sticks to a heavy bowling ball that was initially at rest. Then both roll off with how much momentum? This is not a trick question. Momentum is conserved, so the answer has to be what? Conservation momentum. 2 units. Right? So 2 units before the collision, 2 units after the collision. But really, that question is just a setup for this one, which is a little bit more involved, takes some more thinking. What if instead you have a bouncy ball with 2 units of momentum? The bowling bounces off a bowling ball. Huh. How much momentum has just been transferred to that bowling ball? Okay. got 2 winners. So suppose you got this this bouncy ball coming in with 2 kilogram meter per second. And now if that was putty, then it glides, sticks, inelastic, the whole thing moves off with 2 units of momentum. Okay, so no big deal. But a bouncy ball might go like boing, like bounce off. Suppose it bounces back with, say, -1 kilogram meter per second. It's just like rebounding, right? Boing, right? So guys, what was the change in momentum of that ball? Yeah, you guys see 3, let's say if I take the opposite value, like 3 kilogram meter per second. Okay. So how much momentum was transferred into that bowling ball? 3 kilogram meter per second. Okay, guess that? Okay. Because the impulse is equal and opposite for both, right? Or if you like, before and after momentum accounting, there was 2 units of momentum before, right? 2 kilogram meter per second. And then isn't -1 plus 3 also 2? So that is equal to that. You see that? Okay. Now there is an upper limit on this. Like if you say like, well, if it's perfectly elastic, can it rebound with like -2? Well, if you took it to that, then at some point you would violate conservation of energy. So you have to be careful with the numbers there. But yeah, like more than 2 units. The force that accelerates a rocket into space is exerted by the How about the exhaust gases? You guys like the exhaust gases? Right? Exhaust gases shoot one way, rocket goes the other way. Right? Exhaust gases, yeah. Cannonball shot from a long barrel cannon travels faster than one from a short barrel because it receives a greater what? It might have an equal force, but if that force acts for a longer time interval, why does a rifle have a long barrel? Why does artillery have a long barrel? Because that force time is extended, so greater impulse. 2 kilograms times 3 meters per second is how much momentum? Yeah. Ooh. 4 kilograms with 20 kilogram meter per second. What's the speed? 20 divided by 4 is 5 units of velocity, right? 5 meters per second. Right? And when somebody's moving 6 meters per second, has 24 units of momentum. What's its mass? 24 kilogram meter per second divided by 6 meters per second gives you a mass of 4 kilograms. Nice. This question, we've got Granny collides with her tiny grandson Ambrose. But this question is weird on multiple levels. So the post-collision speed will be greatest when it's inelastic or when they boing bounce off elastic. Where's greater force associated with? You guys remember that apple bouncing off the ground? Right? Or maybe that bouncy ball bouncing off the bowling ball? Right? Isn't there more force associated with bouncing, right, compared to colliding and sticking? There is. There's more force associated with bouncing, right, and also greater post-collision velocity. Right? You guys remember that too with your those collision carts? If they were boing bouncing off each other, you could get carts to sort of like speed up possibly. Right? If all people, animals, trains, trucks began to walk towards the east, right? The Earth already rotates towards the east. It's already rotating east. So if everything on the surface started to walk that way, then which way would they be pushing the ground beneath them? Backwards toward the... Earth spinning this way, west to east. If everybody on the Earth, like that giant guy right there, starts walking east, which way does he push the ground beneath him? A little bit towards the west, which does what to the Earth? Slows it down a little bit. Now, the Earth and everything on surface is a closed system. So when everybody comes to a stop, then the Earth just goes back and does whatever it was doing before. So this is not a permanent change. But well, this is kind of a theoretical question, or if, I guess if you had like a tiny planet like from Rick and Morty or something, right? You're like walking east, and yeah, maybe something like that. With the bronze, Paul Hewitt. Who beat Paul Hewitt? Oh, Tom on. And with the gold, Juliet. Right, who are our runners up? We got X and Fidela. Right, nice stuff. Oh, and just in time, we got this in. All right, you guys have a good Veterans Day, and I will see you guys on Friday for